the last section, we talked about how you can use the derivative to help you determine where a function is increasing or decreasing. And today we're going to continue on that theme and talk about how we can use the second derivative to tell us more about the shape of a graph. So let's start off by talking about what we mean when we say concavity. So the concavity of a graph is really just describing how the curve bends. If the curve is sort of bending upwards, then we say it's concave up, and if the curve is bending downwards, we say that it's concave down. So to give you a few examples, something like a parabola with a positive x squared coefficient would be concave up. We can see that it's sort of bending up. Something maybe like this also, right? So this is some kind of a, looks like 1 over x, or just the positive values of 1 over x, for instance. Or even something that's only, let's say something like e to the x, right? Looks something like this. This is concave up as well because the curve is sort of bending up. And we say that a curve is concave down if it's bending down, right? So a parabola with a negative leading coefficient would be concave down, or maybe something like this. Or even the ln function like this. ln of x looks like this. These are all concave down functions, or concave down graphs. Of course, a function doesn't have to always be concave up or always be concave down. A pretty standard example of that would be something like this function here, right? This, of course, is the function f of x equals sine of x. And this function starts concave, or if you think about it starting at 0, starts off concave down, and then it switches to concave up, and then it'll switch back to down and up again, and it's just going to cycle between being concave down and concave up, and it looks like it switches pretty much at every pi units, right? So we have concave down from 0 to pi, and then we have concave up from pi to 2 pi. And similarly, going in the other direction, it's just going to keep switching between concave up and concave down. So a natural question to ask is, given a particular equation, how do we know where that function is concave up or concave down? Now, it's probably better if we can have some sort of a formal definition for what it actually really means to be concave up, because just saying that it curves up or it curves down can be a little bit ambiguous, especially if it's sort of hard, if you don't know what the graph looks like ahead of time. So the way that we define concavity is we say that if a function f is differentiable on an interval from a to b, well, we say that f of x is concave up on that interval if the derivative is increasing on that interval. And we learned in the last class that a function is increasing on an interval if its derivative is positive. So f prime is going to be increasing on an interval whenever the derivative of f prime, in other words, the second derivative of f, is positive. So this is really how we're describing concave up. We're saying the function's concave up on the interval if its second derivative is positive. Right? And on the other hand, we would say that a function is concave down on an interval a to b if its first derivative is decreasing. And we know that a function is decreasing when its derivative, in other words, the second derivative in this case, would be negative. So we're going to look at the second derivative to determine whether the original function f is concave up or concave down. So just like we had the increasing and decreasing test in the last section that told you about where the original function is increasing and decreasing by looking at the sign of the first derivative, we get the concavity test here, which says if the second derivative exists on an interval and the second derivative is positive on that interval, then we know that f is going to be concave up on that interval. Similarly, if f double prime is negative on an entire interval, then f will be concave down on that interval. So let's try to look at an example and see if we can use this concavity test to determine the concavity. So this is a pretty simple example. We're just going to look at the function f of x is equal to x cubed. Now the concavity test tells us we need to look at the second derivative of this function, right? First derivative is going to tell us where it's increasing and decreasing. Second derivative is going to tell us the concavity. So if f of x is x cubed, then that means f prime of x is going to be 3x squared. And f double prime of x, the derivative of the derivative, is going to be 3 times 2 is 6x to the 1 power, or 6x. So we could sort of break up the real number line just like we did on the increasing and decreasing test, but this function itself, the second derivative, 6x, is so simple that it's probably easier just to graph it to determine where this function is increasing and decreasing. This is just a linear function. It doesn't tell us the y-intercept, so the y-intercept is 0. And it's a steep function because it's 6x. So the graph is going to look something like this. Okay, now the concavity test says anywhere this second derivative function, so anywhere this line is positive, meaning above the x-axis, we'll have that the original function is concave up. So where is this positive? Well, it's positive. It's above the x-axis from 0 to infinity. F double prime of x is above the x-axis, so it's positive. And on the other hand, the function's below the x-axis for all x values that are negative. So on the interval from negative infinity to 0, we have that the second derivative of x is negative. So using this concavity test, anywhere the second derivative is positive, we know that the original function f is concave up. And so on this interval from 0 to infinity, we have that the original function f of x, which is x cubed, is concave up. And anywhere the second derivative is negative, we have that the original function f is concave down. So we have that the function f of x equals x cubed is concave down on the interval from negative infinity to 0. Right, and we can sort of look at the graph of x cubed just to make sure that this sort of makes sense with what we know about this function. The x cubed function looks something like this. Right, so hopefully we could buy that, right, that this function is concave down here and concave up here. Okay. So it changes concavity at this point x equals 0. We call that point where the function, your original function, changes concavity, an inflection point of the graph. So we say that a point c, f of c, in our last one it was 0, 0, is an inflection point of f if the concavity changes from up to down or vice versa at that point c, f of c. Now keep in mind, the only way that your graph could change from concave up to concave down is when the second derivative changes from being negative to being positive or vice versa, right? Because the second derivative sign corresponds to the original function's concavity. And so the only place we can have an inflection point, the only potential inflection points are the points where f double prime of x is either equal to 0 or undefined. Because the only time f double prime could change from negative to positive is if it passes through 0 or if it's undefined. Okay, so with that in mind, let's look at one more example here. We're going to find all inflection points for the function f of x equals cosine of x on the interval from 0 to 2 pi. Now you may think that you already kind of know how to do this, right? You could just draw a graph and see where it's changing from concave down to concave up. But just for the sake of making sure we understand the concavity test, let's try to use the concavity test to determine the inflection points, right? So the inflection points can only really occur when the second derivative of f is either equal to 0 or undefined. So let's start off by finding the first and the second derivative. The first derivative of cosine is negative sine. So the second derivative would be the derivative of negative sine. Well, the derivative of sine is cosine, so the derivative of negative sine would be negative cosine. Okay, and so according to what we have up above, the only possible inflection points are where the second derivative is equal to 0 or undefined. Of course, negative cosine of x is never undefined. So the really only possible inflection points would be the x values in the interval from 0 to 2 pi, where the second derivative, that negative cosine of x function, is equal to 0. Okay, this is what we're trying to solve here. We're trying to solve for where is negative cosine of x equal to 0. Well, for that, we can sort of rely on the unit circle. Remember, we're looking for points on the unit circle where negative cosine of x is equal to 0. So multiplying both sides by -1, we're also looking for points where cosine of x is equal to 0. Okay, so we're looking for points on that unit circle that have an x value. We need points on unit circle with an x value of 0, right? Because cosine represents an x value. So the only points on the unit circle with an x value of 0 would be, well, x value of 0 means you can't go left or right, so it's either going to be this point up here or this point down here. Right? This is 0, 1, this is 0, -1, and the angles that correspond to those points would be this angle here, this 90-degree angle, which is pi over 4, and then this larger angle down here, which is going to be 3 pi over 4. So our only possible inflection points would be pi over 4 and 3 pi over 4. Okay, so the concavity could be changing there. However, we don't really know for sure that the concavity is changing there because sometimes you have these potential inflection points that don't turn out to be inflection points at all. So to test whether those are actual inflection points, we need to know, is the function actually changing concavity there? So we're going to set up a test just like we did for the increasing and decreasing test, where we put our possible inflection points on a number line, so pi over 4, 3 pi over 4, and then we test a point within each interval and try to determine whether the second derivative is positive or negative. Because remember, wherever the second derivative is positive, your original function will be concave up. And anywhere the second derivative is negative, the original function will be concave down. So, can you see this? Oops, okay. So I set up my number line here, and keep in mind that we're only looking at the interval from 0 to 2 pi. So I'm just going to put 0 and 2 pi here. So my intervals then are going to be 0 to pi over 4, pi over 4 to 3 pi over 4, and finally 3 pi over 4 to 2 pi. Okay, and we test a point in each interval by plugging it into the second derivative function. So I need to choose some angle between 0 and pi over 4. In other words, choose some angle over here somewhere. Oh no. Oh no, no. Oh, I messed this up. Oh, uh-oh, I'm sorry. Just realized a mistake, my bad. This angle is not pi over 4. Ding dong. Alright, this is, pi over 4 would be this 45-degree angle. This is pi over 2. I don't know what I was thinking. This has been a long week, my friends. Alright, pi over 2. And this angle here, this 90, 180, 270-degree angle would be pi over 2, 2 pi over 2. This would be 3 pi over 2. Oof, wow, good save there. Okay, so pi over 2 and 3 pi over 2 are our two possible inflection points. So this should be pi over 2 and 3 pi over 2. So just fix all of these in your notes if you're following along. I'm very sorry. I'm glad I found this before I finished the video. Whew, all right. So this is pi over 4, right? So this angle here is pi over 2, And so if we want to test a point in this interval from 0 to pi over 2, you'd want to pick something like this. This angle here is the angle pi over 4. Oof. All right, so let's plug pi over 4 into our f double prime function to test whether the sign is positive or negative. Can you see this? Okay, so when I plug in pi over 4 into f double prime, we're going to get negative cosine of pi over 4. Okay, well, cosine of pi over 4 is up here, so it's going to be positive. So this is going to be negative times cosine of pi over 4, which is positive, which means this outcome here is going to be negative. Okay, that tells us that since your second derivative is negative on this interval, that means my original function f is going to be concave down. Okay, now we're going to do the same thing in the second interval. We want to test some point that's in between pi over 2 and 3 pi over 2. So choose some angle between pi over 2 and 3 pi over 2. I'm going to choose pi. I'm going to plug in pi into the second derivative, and I'll get negative cosine of pi. This is going to be negative times cosine of pi is negative 1. So this ends up being something positive, which means my original function f is going to be concave up on this interval. And finally, choose a point between 3 pi over 2 and pi, something like over here, 7 pi over, what would this be? Pi over 4, so 2, 3, 4, 5, 3, 4, 5, 6, 7 pi over 4 would work. It'll be negative cosine of 7 pi over 4. That's negative times cosine of this point is the x value. The x value is something positive. So it's a negative times a positive, which is negative. So since the second derivative is negative on this interval, your original function is going to be concave down on this interval. Okay, and so your function does indeed change concavity at pi over 2 and at 3 pi over 2. The concavity does change from down to up, and then again from up to down at pi over 2 and at 3 pi over 2. So we have inflection points at pi over 2 comma something, and at 3 pi over 2 comma something. Right, so something to point out is that when we define an inflection point, the inflection point is both the x value and the y value. All right, so to figure out the actual inflection point, we need to plug these x values, pi over 2 and 3 pi over 2, into your original function, the cosine function. So just as an aside up here, we have cosine of pi over 2 is equal to the x value there, which is 0, and cosine of 3 pi over 2 is equal to the x value down here, which is also 0. Okay, so the inflection points are at pi over 2 comma 0 and 3 pi over 2 comma 0. Okay, so hopefully we see how this is similar to the increasing and decreasing tests that we were doing. The only real difference is we're following the same steps, but looking at the second derivative instead of at the first derivative. So, in the next video, we're going to go over a few more examples of looking at the equation of a function and using that to determine the concavity as well as the increasing and decreasing intervals.